Welcome everybody to this Facebook live stream where we explore the interaction between science and the Christian faith. My name is Dr. Fuz Rana. I am a biochemist, a Christian apologist. I'm also the Vice President of Research and Apologetics at Reasons to Believe, which is the organization that sponsors this live stream. If you want to know more about our organization, I would invite you to go to our website at www.reasons.org to learn more about our organization. Today's question is, have origin of life researchers discovered a computer algorithm that can explain the origin of life? And this question is inspired by recent work published by a team from the Polish National Academy of Sciences who've developed a computer algorithm they call alchemy that they argue gives key insight into the early events in prebiotic chemistry and the early events in chemical evolution leading to the origin of life. This work is an exciting study that was published recently in the journal Science. So we're going to take a look at this work and what does it mean for chemical evolution and the origin of life question. Before we do that, I just wanted to say hello to all of you who have watched these Facebook live streams in the past. I took a hiatus from doing these live streams simply because I have been in lockdown mode trying to finish the manuscript for my next book, which has as its working title, Fit for a Purpose. In this book, I make the argument that there is an anthropic principle that we see in the design of biochemical systems that complements the anthropic principle that we see in cosmology. So this book is due to be published in October of 2021, so stay tuned for more information about that book. And while we're on the topic of talking about new books, there is a new book that is being released this month in October of 2020 from Reasons to Believe, entitled Thinking About Evolution, and I'm one of the co-authors on that book. So if you want to know more about how you can get a hold of this exciting new book from Reasons to Believe, go to our website again, www.reasons.org, and there is information about how you can get your copy of Thinking About Evolution. Okay, well, without any further ado, we're going to go ahead and get started with the live stream. But as we're working our way to getting things going, as is customary, I would love for those of you who are watching this live stream, whether as a recording or live, to check in, say hi in the comment section. Let me know who you are and where you're listening from. This is valuable information for us to have, but it's also a great way for me to get to know who's watching these live streams. Also, I'd love to know what your perspective is on this discovery and on the origin of life problem. Please feel free to offer your thoughts, your comments, your perspectives. Whether they agree with me or not, I want to create a milieu where people can feel free to talk in a civil way about really critical issues relating to science and the Christian faith. And then last but not least, if you've got a suggestion for a show topic for a future episode, please put it in the comment section. I read all of your comments, even though I may not be able to reply to each and every one of them. Okay, without any further ado, let's go ahead and get started with today's live stream topic. Have scientists developed a computer algorithm that can explain the origin of life? Well, when it comes to the origin of life question, I think it's safe to say that this is on the verge of being an impenetrable scientific mystery. And to be clear, origin of life researchers have done an enormous amount of work over the last 70 years or so. And this work has offered important clues as to how chemical evolution could have transpired on the early Earth. And the work in origin of life research really began in 1953 when Stanley Miller and Harold Urey published the results of the famous Miller-Urey experiment, or the spark discharge experiment, where Stanley Miller simulated the conditions of the early Earth's atmosphere and showed that electrical discharge through the headspace of a gaseous mixture that again mimicked the Earth's atmosphere could generate in short order some very interesting organic compounds, including amino acids, which are the building blocks for proteins. And since that time, a lot of the work in the origin of life is primarily focused on laboratory studies where origin of life researchers are trying to mimic the conditions of the early Earth, and in doing so try to identify different chemical and physical processes that in principle could contribute to chemical evolution and the origin of life. And over the last 60, 70 years, origin of life researchers through this approach have identified chemical pathways that could make most of life's building blocks, have shown how these building blocks could assemble into polymeric materials, have shown how they could evolve from these polymeric materials interesting functional molecules like a wide range of ribozymes made up of RNA. They've shown how you could generate amphiphilic materials that could in principle form the very first protocellular structures that could encapsulate small molecules and even polymeric materials. They've shown how autocatalytic cycles could potentially develop under conditions that would mimic hydrothermal vent environments. They have developed self-replicating systems. And so much of the chemistry and physics that in principle could contribute to the origin of life has been identified by origin of life researchers. But yet nobody really understands how the origin of life could have transpired through chemical evolution. This work is considered to represent disparate clues, disparate pieces to a very complex puzzle that they can only fit together in a very limited extent. Nobody really quite understands how chemical evolution could have generated the origin of life. And there's a number of reasons for this. One is that the work that's been done in the laboratory has been primarily proof of principle studies or mechanistic studies. Much of the work when it comes to prebiotic chemistry is questionable in terms of its geochemical relevance. That is, these reactions work marvelously well in a laboratory when there's an organic chemist superintending the reaction. But when you start to imagine how that chemistry would transpire and translate under the conditions of the early Earth, it raises some significant questions about geochemical relevance. And so this is a big sticking issue right now that origin of life researchers have recognized and are actively trying to address. Another shortcoming is that much of the work that's been done has been focused on isolated chemical or physical chemical reactions or physical processes. And of course, the early Earth's environment would be a chemically and physically complex setting, and that complexity is not factored into these prebiotic chemistry reactions. And again, many people see this as a significant shortcoming and means that maybe origin of life researchers are actually missing some important clues about how chemical evolution could transpire by not addressing the chemical complexity of the conditions of the early Earth. In fact, early on, Stanley Miller recognized this as a problem and called for what is known as a Beilstein type of reaction to try to understand the origin of life. And what's meant by that is a Beilstein reaction involves throwing a large number of chemicals into a flask and letting those reactions run, and then trying to sort out what has happened in that complex chemical environment. The problem is that this becomes an analytically intractable problem, given the technology that we have in analytical chemistry. And so people recognize the importance of doing this kind of work, but have not really been able to do this for practical reasons. And even if you could somehow analytically characterize that kind of a complex system, it's going to be very difficult to tease out what are the individual chemical reactions that it's responsible for what is happening in this complex chemical mixture in terms of the chemistry and the physical chemical processes that are taking place. Now, in 2007, a group from the UK, headed up by a chemist by the name of Sunderland, took a first step towards looking at the complexity of the Earth's environment and the impact that could have on prebiotic chemistry when they began to intermingle some of the chemical routes they think could have produced carbohydrates with some of the chemical routes that they think could have produced nucleobases. And they discovered that by doing so, they could identify a 5-step reaction sequence that could go from relatively simple molecules to actually 2 of the 4 ribonucleotides. This was an extremely exciting development that indicated that actually by increasing the complexity of the prebiotic chemical reaction, you actually create opportunities for very interesting chemistry to take place that you just simply would not be aware of if your focus was primarily on isolated chemical reactions. Now, when I was at ISSL 2017, which is, ISSL stands for the International Society for the Origin of Life, in 2017, this conference was held at UC San Diego, which is just a couple of hours south of where I live. So I went and spent a week on the UC San Diego campus attending this ISSL conference. And one of the things that I noticed that represented kind of a new approach to studying prebiotic chemistry was a number of studies where researchers were doing these Beilstein type experiments where they were creating these complex chemical mixtures in the laboratory and then watching what happens to those mixtures over time, showing that these systems can actually behave in predictable ways in response to changes in temperature and pressure and pH. And that this suggested that this complex chemical milieu could begin to display emergent properties in response to changes in the environment. And this is considered to be rather exciting, though again it becomes a chemically intractable problem to try to make sense of. So it's in this backdrop that the work by the scientists from the Polish National Academy of Sciences takes place. And what these researchers did is perform what's called a computer-assisted organic synthesis, where they're doing chemistry in silico. And they developed an algorithm they called alchemy, which essentially mimics the chemistry that would take place hypothetically on the early Earth, starting with relatively simple gaseous compounds like water, hydrogen sulfide, ammonia, methane, nitrogen, carbon dioxide, and hydrogen cyanide and ammonia. So those were the starting materials, and they essentially developed this computer algorithm in which they programmed in all the known prebiotic chemistry reactions that had been discovered up to this point. And from that, they identified a set of 614 chemical rules that they could then organize into about 70 different families of chemical reactions. And then they essentially developed, as part of their algorithm, a way to identify certain incompatible chemical groups. In other words, functional groups that simply are not going to react with each other. And they fed those rules into their algorithm, and essentially they just let it rip and look to see what essentially would be produced. And after they generated this mixture, this again computer-assisted in silico mixture of products from these starting reactants, and again mimicking the conditions of the prebiotic earth, and using these different chemical rules, they excluded compounds that would be kind of ludicrous in terms of their chemical structure. There's no way that these chemical compounds could ever exist if they were indeed hypothetically generated by chemical reactions. And then once they had this set of products, they took those products along with the original starting materials and they ran another generation of reactions. And they repeated this over and over and over till they generated 7 generations of chemical reactions, again, iteratively, each time creating greater and greater complexity. And what they discovered is that through this process, after 7 generations, they were able to generate about 37,000 different chemical compounds. But of those 37 compounds, only 80 of them actually were biotic compounds, compounds that you would see in biological systems. The rest of them were, again, abiotic compounds. And the compounds that they generated were about a molecular weight of 300 or less. So they were only looking at small molecules. Of those 80 compounds that they generated, 41 of them were peptides, which would be formed by reacting amino acids together to form either di or tripeptides. And they noted that the number of peptides and the size of the peptides increased as they went from 1 generation to 7 generations, which is what you would expect. So of these 80 compounds, 40 of them would have been building block materials, and the other 40 would have been some versions of peptides formed from differing amino acids. Now, one of the things that they noted that I think is really interesting is that the 80 biotic compounds shared certain chemical properties and physical properties compared to the abiotic compounds. They were essentially more thermodynamically stable. They were hydrophilic, meaning they were much more likely to dissolve in water. They had very little hydrophobicity to their structure. They had relatively few chemical groups, and the chemical groups they had were relatively unreactive, and they had a balance of chemical groups that could take part in hydrogen bonding interactions, where that there was a balance between hydrogen bond donors and acceptors. Now, this is really intriguing because it suggests that these biotic compounds that are produced have highly unusual properties. So a really small segment of the compounds that they produced are biotic, and those compounds that are biotic have, again, a really unusual suite of chemical properties that make them ideally suited for their role in biochemical systems. In addition to that, they discovered synthetic redundancy with respect to those biotic compounds. As I mentioned, they used 614 chemical rules to kind of guide the types of reactions that the algorithm could allow and explore. But those 614 rules grouped into families of 70 reactions, 70 different reaction families, if you will. They discovered that they could eliminate almost 35, almost half of those reaction families, and still generate all of those biotic compounds. Interestingly enough, with the abiotic compounds, they could only eliminate 8 of the reaction families and still generate the 37,000 abiotic compounds. So this indicates that these biotic compounds have very unusual properties, and the chemistry that would be in principle available on the early Earth could produce these compounds through a variety of different synthetic routes. They also discovered that there were certain compounds that would form what they called reaction hubs. Things like isocyanic acid, cyanoacetylene, and formic acid formed these hubs from which a number of different chemical reactions could take place, producing a wide range of different chemical compounds. And they think the existence of these chemical hubs may actually explain in part the synthetic redundancy that they were noting. Now, one of the things that they found to be really interesting is that all of the prebiotic reactions that have been discovered by Origin of Life researchers over the last 70 years were on full display in their algorithm, in the types of products that would be produced through this computer-assisted organic synthesis. And of course, that isn't surprising because they used the chemistry for prebiotic reactions to kind of develop these rules that they use to guide the operation of the algorithm. So in a sense, that isn't that surprising of a result. They also discovered some prebiotic reactions that have not yet been discovered by origin of life researchers. Now, there are two categories of these newly discovered reactions. One of them they call trivial synthetic routes, which really consist of pathways that really appear to be cobbled together from pre-existing prebiotic reactions that we already know exist. But there were a handful of reactions they discovered that nobody was aware of, that no one had ever discovered, that were novel reaction pathways. And in fact, they went into the lab and they demonstrated that these pathways they discovered actually would perform the chemical transformation that the algorithm indicated that it would. So they verified their results in the laboratory through some synthetic work. Now, another thing that they found really interesting was a number of emergent properties that came out of this complex chemical system. One of which is that the products of one generation of chemical reactions could actually serve as catalysts for the next generation of chemical reactions, meaning that as the complexity of the system increases, you generate compounds that now can function as catalysts that make available new chemical routes that wouldn't otherwise be available if it wasn't for the catalytic activity of these of the products of these chemical reactions. So this is an exciting development that again suggests an emergent property. They also discovered the creation of self-generating cycles. These are not self-replicating cycles, but kind of self-regenerating cycles that would sustain themselves as an ongoing cycle of chemical reactions. They also discovered self-regenerating cascades of chemical reactions as well. And then last but not least, they were able to show that they could generate things like fatty acids and alpha hydroxy fatty acids, which are materials that are amphiphilic that could serve as the materials that could build primitive cell membranes. They also discovered the generation of some peptides that actually had amphiphilic properties, where part of the peptide was hydrophilic, meaning water soluble, part was hydrophobic, meaning water insoluble, and they could serve as surfactants as well, meaning that out of these reactions, you're generating materials that could actually now serve to create kind of protocellular type boundaries that provide the means to encapsulate some of the chemistry that is being generated through this process. So this is a really exciting study that I think is science at its very best. And it really is pointing us in a new direction when it comes to prebiotic chemistry and origin of life research. It's really ushering in a new era, I think, in prebiotic chemistry. And this is actually really very exciting to see what's going to come from this. And what it also shows is that there is value in doing a Beilstein reactions, that maybe some of the clues to the origin of life mystery are going to be found in the complexity of the chemistry, not in the simplicity of the chemistry, and that through the use of computer-assisted organic chemistry, it may provide the means by which to interpret some of these Beilstein reactions that people are beginning to explore. Because we're now beginning to have available to us the technology to allow us to analyze these complex chemical mixtures rather quickly and in a time-efficient, cost-efficient manner. But again, how to make sense of the results is going to be a real problem. But this problem could, in effect, be resolved through the use of computer-assisted organic chemistry. So really, very exciting results to be certain. Now, does this work really move us any closer to understanding chemical evolution and the origin of life question? Well, as exciting as this work is, I would argue that it is giving us proof of principle insight into the value of chemical complexity when we're trying to understand what could happen under the conditions of the early Earth. But I would also point out that this work, again, has been done in silico. It's not work that's been done in the lab. And much of what they've done in this work is, again, an artificial set of conditions, they didn't take into account, for example, things like the concentration of the reactants. And this is going to be really important because many prebiotic reactions actually require relatively high concentrations of the reactants for the chemistry to proceed in a productive manner. And under the conditions of the early Earth, there's very real concern about essentially diluting out the prebiotic molecules to such a degree that you're not going to have the levels, the concentrations that you're going to need for the chemistry to take place. They also didn't include kinetic factors. How fast does the chemical transformation take place? This is actually really important because if some chemical reactions are relatively slow, it may mean that they are never going to happen under the conditions of the early Earth. And then also, they didn't take into account the diffusion because if these reactions are taking place, again, on the conditions of the early Earth, there may be need to diffuse reactants from one location to another in order for that chemistry to transpire. They failed to take into account the types of energy sources that would be available on the early Earth. They did not take a look at the effects of minerals or phosphate chemistry, nor did they take into account stereochemistry or the idea of chirality, which is, again, a very important factor. So the bottom line is that this is really interesting proof of principle work that I still think lacks, in large measure, geochemical relevance. But again, having said this, this is really a very exciting work that I think is pointing us towards a new era in prebiotic chemistry. Another concern that I have with this work is that what's known as the homopolymer problem. And this is a problem identified by Robert Shapiro, the late Robert Shapiro, who was an origin of life researcher of some renown. And he pointed out that to go from building block materials to polymeric systems in which you now have molecules that could essentially function as biocatalysts, that required producing materials that had a repetitive backbone where the repeating unit was identical from subunit to subunit. This is called a homopolymer. And he points out that in a chemically complex environment, generating a homopolymer is a huge problem. And so while chemical complexity can actually do some really interesting things in terms of making available a wide range of prebiotic reactions, it's actually going to create problems as you try to go from building blocks to polymeric materials because of this homopolymer problem. And in fact, when you look at some of the peptide products that were produced, it demonstrates this very point because these peptides were adducts of amino acids that have reacted to form, again, dimers and trimers and tetramers, but that these were not peptides that displayed a homopolymer backbone, but rather showed bonding of carboxylic acid groups with side groups and things like that. Also, the surfactants that they generated are interesting, but we know from other prebiotic studies that just because you have surfactants around doesn't mean they're going to assemble into single bilayer vesicles, which is what you need for protocellular entities. In order for that to happen, you have to have very precise compositional makeups of the surfactant systems, and you have to pay very close attention to the environmental conditions. The pH is critical, the salinity of the system is highly critical, the types of counter ions that were around. And so to me, this is, again, very interesting work, but when you start envisioning how you go from this complex chemical milieu to now creating greater degrees of emergent properties and self-organization, I think the question still remains, how do those types of transitions take place? Now, let's just say one final point, then I'll bring everything to a close. Let's just say, for the sake of fun, that we just assume that this work actually gives strong validation to the idea of chemical evolution. That let's just say, for the sake of argument, that this work demonstrates the validity of chemical evolution. Well, it doesn't mean that you escape the theistic implications that are associated with the fact that we don't understand how to create the complexity you need to go from molecules to the very first cells. Because, as I mentioned, there's a real problem with regard to geochemical relevance, and part of that problem connects to the fact that in the lab you have researchers that are jimmy-rigging the system in such a way to have carefully controlled conditions that ensure the success of the reactions in the lab. And of course, when you translate yourself to the conditions of the early Earth, what's missing is the presence of organic chemists to superintend these processes, to exert the type of control you would need for that chemistry to be productive. And this is, in effect, the issue with the homopolymer problem, or with the generation of surfactants that would then assemble into single bilayer vesicle-type systems. And in effect, what you could argue is the work in prebiotic chemistry demonstrates the necessary role intelligent agency must play in affecting chemical transformations that could contribute to the origin of life. But even if you set that whole set of arguments aside and just assume that this work provides validation for chemical evolution, there are still very interesting theistic implications. For example, as this work demonstrated, that there is this synthetic redundancy such that you're going to generate these 80 or so biotic compounds, and that these compounds, again, can be made by a number of different chemical routes. And on top of that, these biotic compounds have a unique set of properties that cause them to stand out compared to 37,000 different abiotic compounds that were generated in this computer-assisted chemical reaction, or set of chemical reactions. And this unique set of properties is exactly the set of properties that are needed for these materials to be useful for life. And so this is a really eerie anthropic coincidence that prebiotic chemistry seems to be jimmy-rigged in such a way that inevitably the building block materials needed for life are going to emerge. In other words, it looks as if there are these physical chemical constraints that arise out of the laws of nature themselves that essentially are forcing prebiotic reactions to particular endpoints, and those endpoints happen to be just exactly the endpoints that you would need conceivably for a chemical evolutionary origin of life. It's very easy to envision an alternative scenario where the constraints of the laws of physics would generate compounds that would have properties that cause them to stand out, but those properties would be such that they would be of little value for chemical evolution and for the origin of life. And so, in other words, you can't get away from the theistic implications of this work. Either you go down one path where you recognize the necessary role intelligent agency must play to affect success in prebiotic reactions, or you acknowledge these anthropic coincidences that seem to be connected to prebiotic chemistry, suggesting that there was a mind behind the universe that at the very beginning prescribed the chemistry and the physics such that the origin of life would in effect become inevitable. So very interesting work, to be certain, that has that's fascinating from a scientific perspective, but also fascinating when you start thinking about the theological implications of this work. Okay, I'm going to go ahead and bring things to a close. Thank you for watching. Please take a moment again to check in. Let me know who you are, where you're watching from. Also, visit our website at reasons.org and learn how you can get a copy of our new book, Thinking About Evolution. And then last but not least, I just want to leave you with these words. The more that we know about science, the more that we have reasons to believe. God bless you. See you next time.